the display of the quality, of the stability graph of the internal standard really is only, it is important to see that it was nice and flat. What we are looking for are big variations greater than plus minus 20%, which are those lines right here. And we can see that our internal standard performed well. They should be, because the samples are all pretty much the same samples in the same matrix, and the internal standard is always introduced at the same rate, so they should not vary. They will vary if the matrix changes dramatically. So if we have a very concentrated sample in a very concentrated acid or very concentrated salt solution that's very different from all the other samples that we measure, that will be reflected in how much we detect of the internal standard, and we will see that here. Not in this case. Now the quality control is when we measure throughout the measurement, and this is labeled with Europium 10. It's a quality control. It has all elements at about 10 ppb in this case. We measured this quality control throughout the entire sample measurement about 3 times, at minimum of 3 times, and this is what we determine our coefficient of variance from. What we want to do is we want to measure one sample 3 to 4 times and then average that out and say, okay, the average deviation in this, average standard deviation in this sample was this and this, and then we'll divide that by the concentration, and we also have a relative variance of our sample, and that's what we call the coefficient of variance, and that's what we report with our measurement. It gives us an idea of whether there was if there was a drift in the instrument, or if there was a big variation between each measurement from time to time. It's just a reflection of how well our measurement performed. It's not a measure of the accuracy of our data, but it is a measurement of how accurate, or it's a measurement of how consistent our data was. In order to display that, we have to go to method and just go to full quant. So we will go to method, and we'll click on the window and not on the arrow in this case. And we'll go to full quant outlier. And full quant outlier we can see, so the ISD recovery percentage is 80 to 120%. We have to, for some reason, fill this in for the quality control every single time we do this. We do return to batch at a glance, update data analysis, yes. And then you can see here the process button has an exclamation mark and it's red here, so we click this once. So we process this, and this comes up with a bunch of errors, but I'll explain this in a second. And then we'll just have to switch once, twice, and then it's there. So what is happening here is that, in fact, we have defined the values for the quality control wrong in our full quant. And I should go back and change that. The concentration of the sample that we measured in our quality control, we defined that as 10 everywhere, but it's really, calcium is measured as ppm, so it's not ppm, it's 10 ppb, so it would be 0.01 for calcium. For the rest, it was closer to 12, so we'll just do 12. And here's another trick for everything that's in MassHunter. If we have the same value that we want to fill throughout a column, we can just like select all of them, right click, and then select fill down, and it will fill down all those values. That's a very neat thing about MassHunter, and I wish Excel had the same thing. also for sample, when we put in samples in MassHunter and the initial measurements and so on and so forth, but it's very helpful. Okay, so we return to batch at a glance. And then again, process comes. So you can see that right now, the outliers, they will show up in red. So if we process batch now, you'll see these are gone. And if we look at our quality control now, we can see that calcium is like high, but there's like a limit of calcium, so I'm not worried about it. But we can see that it's actually a very nice curve. It's very stable. So this, we can export all of this as graphs. So we just right click and then we just have copy and paste. So these two are exported as graphs. Every single element will be exported as a graph, also copy and paste. And the tables will be exported as tables. So we will export each table as a graph. So in this case, we will export the table, will automatically go to the directory that we opened the batch from. For these tables, and that is something that I have outlined in the Word document already. So we just hit export table, and then we choose any date, we choose any name, it doesn't matter, and save it. But we directly copy the table and put it under the corresponding element in our main result table that we will forward to our users. The other thing that I wanted to mention here real quick is the other neat thing is the total dilution factor. So we usually put in the total dilution factor in this batch table and then export the data as already considered by the total dilution factor. It's just a nice, easy thing to do in this. In this case, the dilution factor was 2 for everything. But there are times that we have more complicated dilution factors, and so I just wanted to show you the different options that we have. So we can just put in a number, 2, for example, or what we can do is like we can double click on this, and then we'll get a calculation of the dilution factor window, and that's pretty neat. So let's say this was actually a sample that we digested. And so let's just say this was a sample where we had 100 milligrams of sample. We then took it up in altogether 4 milliliter of solution, or 4 milliliter of solution. And that 4 milliliter of solution, we diluted another 6 times when we actually measured the sample. What is the final dilution factor? Easy here. What we do here is we just say we had 100 milligram of sample. Our final volume was 4 milliliters, and we diluted these 4 milliliters another 6 times. Our final dilution factor was 0.24. This will give us a unit of a milligram per kilogram. So we cheated a little bit here in the final weight and volume to give us a different unit than usually would come out. But this is just an example of what we could do to calculate the dilution factor. And that's what this is exactly what we do for all samples that we digested. This is where we enter the dilution factor. So this is one easy way to enter the dilution factor. One other thing I just wanted to quickly point out is how can we change these settings that we have up here. Settings that we have up here depends on like how you install how the program is installed. Sometimes we can just right click here, and then there is something that comes up here where we can specify the column settings here. It's not in this menu, and I don't know why. But if we go to settings, and if we go to view column settings, and look at user settings and we go to edit, then we get this screen, and that will be the same regardless. And we can go and change every single screen. So this is what I have, for example, for number 1 for the actual sample. I want to list all of these. I want to list the data file, sample name, acquisition date in this order. For the analyte, which are my elements, I want to see the concentration, the counts per second, and the counts per second relative standard deviation. For the ISTDs, I only want to see counts per second and counts per second for counts per second relative standard deviation. For the replicate data, I don't want to see those. If I look at column setting number 4, all I want to see for the replicate data, I want to see the concentration and the counts per second. For the rest, it's the same. So let's just try to change something. So let's say in column setting number 2 that I really never use for my analytes. Right now I only have the counts per second and counts per second relative standard deviation. Let's just say I also want to know the concentration in here. I hit that add, and then I can click on it. I want to have it displayed first, and I can save it, and then it's saved in my display number 2. And hopefully if I go to display number 2, there it is. I have concentration, count per second, counts per second, relative standard deviation. So this is just a quick intro into the basics of the data analysis. I hope this is helpful.